So what is the job of turbine? To extract energy. What kind of energy? Hydraulic energy, and convert it into what? Mechanical energy. And this mechanical energy is further get converted into what? Electrical energy. But our job is to convert this hydraulic energy into the mechanical energy. Our job is done, and then it is up to electrical engineers how do they convert and all. So we are not worried about that. Only we are worried about is that to convert hydraulic energy into mechanical energy, right? Now, and this is the way, like if I write down the conversion, means hydraulic energy is converted into what? Mechanical, and this further gets converted into what? Electrical. This further gets converted into electrical energy. Okay. And see how we have reached to this electrical energy using hydraulic energy, right? So that is why these are called hydroelectric powers also. Hydroelectric power. Simple, these things are simple, so there's nothing much left here. Okay. So, what are the general uh, construction means a layout? I should say that what is the layout of any general turbine? Like what are the constituents of it? Like, so first thing is that there is a storage tank or a dam where the water is stored, and then we have a turbine, or before that we have uh, penstocks, means we have the pipes which will carry those fluid to the machinery, right? So first thing we need to have is to store the water, means water is stored somewhere. Stored water I can write, there is some stored water, and then these are carried to what I am writing down here is that layout of a hydroelectric power plant. Hydroelectric power plant. Okay. So first thing is we have stored water. Second thing is what? We have pipes which will carry these waters to the turbines. So these are called what? Penstocks. Penstocks means what? These are the pipes of large diameter. And then obviously what do we have is turbines. Turbines. And then we have very important tail race. Tail race means what? Tail race means what? That after turbine, once the water goes through the turbine, then these water get rejected somewhere. Yes or no? Why? Because you need continuous work. So that means that after the hydraulic energy is converted into what? Mechanical energy, then water has no energy left with it. Then this water must be discharged somewhere, right? So it is discharged where? That is called tail race. Okay. So this is the basically a channel which will carry out this water to somewhere else. Got it? So if I draw, then what do we have? Like for any general turbine, what do we have is like if I draw. So what did I say? That we have a dam kind of a structure, right? So we have one dam where some water is stored. Okay, let us draw it here. We have one dam. Okay, and here we have water storage. And what do I write here? This is the dam. Here we have water storage, and this is pen stocks. Like this, these are the pipes which will carry these water through this pipe to what? To the turbines. And here we have nozzles. We'll study about these parts later on. Here we have nozzles fitted here, and through these nozzles, what do we have here is that these will supply water to what? To the turbines. So here what do we have is turbine, and a turbine is basically nothing but there is a, we have studied now that there are curved plates fitted on a means a runner. So this is nothing but that runner, and it have one what number of plates, upon which this water will strike. Got the idea? And then this water gets rejected to what? Tail race. Got the tail race. This is the layout of any general power plant, hydraulic power plant. Okay, I hope it is clear. Okay, now very important things which I am going to discuss here is, please look at carefully. Okay, so this is tail race, means this is the datum level, means here your water has no energy. Okay, and now I will tell you one by one what things we do have. See, here water has some energy, yes or no? So you understand now what do I mean when I say head? Means if I say that 10 meters of water head, 10-meter head of water, then what do we understand? 10-meter head of water means that if you multiply it by specific width, that is rho g multiplied by h, then this is giving you that okay, this is the pressure that at that place we do have. Got the idea? So similarly here what do we define, that this is the gross head. Gross head means what? That this was the total head available at the dam. Getting me or not? This was the total head which was available at the dam. So this is also called what? Head race. First thing, what do I say? That we have gross head, means the total head available at the dam, means whatever the storage you do have, means maybe it is not a dam, just the water storage place. So what is that head available with respect to what? This is now your datum part, right? So this is called hg. Hg means gross head. This is what? Gross head. Okay, first thing clear. Now in your fluid mechanics, you must have heard that whenever there is a pipe flow in the water, means any general flow water, if water is flowing anywhere or any fluid flow, then it has some frictional losses. Yes, means that water is traveling through this through the pipe, then it must be suffering certain kind of what? Head loss. Head loss means what? That this hg which was initially available here, the same head won't be available at this point. Why? Because during this travel, means from the dam to the turbine, this during this travel it must have suffered some frictional losses and major and minor losses also. What are those losses? That like somewhere it must have entered, somewhere it must be trying to exit. That means major and minor losses also, and frictional losses. So all those are accountable for what? The loss in head. So what do I mean? That at this point, means initially by it should have been, means if there was no loss here, you should be able to get that gross head part. But since there are losses, so your head now available will be bit less, and this will not be equal to hg but somewhere less than hg. So this part which is lost is called frictional loss, or in general we call it that head loss, but frictional loss. Why? Because this is the dominating one. So this is the part, if it is lost, then at the turbine entry you have this much amount of head only, and this much amount of head is called net head. Net head net head denoted by whom? H, capital H. Then I can clearly say that this is equal to nothing but Hg minus Hf. Any doubt? Hg minus Hf. Simple. We can write it down by small case letters only, so there's no confusion that where do we write a small and capital. Okay, so net head is clear, gross head is clear, and this loss, this is also clear. Okay, this is dam, this is penstock, this is turbine, this is vane. Okay, and here we do have this part, means if I specify, then this part is called nozzle. This is also very important part, otherwise there will be no focused flow, right? And then we have tail race. Tail race is nothing but a container. You can imagine that this water must fall somewhere, so this is called tail race. Okay, now, so turbine layout, I hope now this is clear. So what is gross head? Gross head, it is the head under which the plant is working. Yes or no? So if I write down gross head, then this is the head under which plant is working, right? Under which the plant is working, and this is used to calculate efficiency of the plant. We'll talk about everything, efficiency of the plant. Okay, now next, net head, the gross head denoted by whom? Hg, and gross head, net head, this is the head, it is the head, it is the head available at what? At nozzle. Yes or no? At nozzle. We have seen now that at this nozzle part, this is the part where we have total head. Okay. So this is the, or what we can say is that this nozzle is at tail race level. Okay, no, nothing to be worried. We'll talk about if any confusion arises, we'll talk. So it is the net head is the available at the nozzle or nozzle inlet, or what we can say that it is the head, it is the head under which turbine is working. See the difference there? What did I write? Is that the plant is working, but here under which turbine is working, there's a lot of difference. Okay, now next thing is, now let us talk about few efficiencies. Okay, very important efficiencies. So efficiencies which are frequently used in a turbine, which has some physical meaning, so I am writing down now, is efficiencies of a turbine. First is hydraulic efficiency. Hydraulic efficiency. Hydraulic efficiency denoted by whom? Neta H. So what do I mean by hydraulic efficiency? It is the efficiency which is the ratio of Power delivered to the runner, power delivered to the runner divided by power supplied at the inlet. What do I mean? What do I mean? Let us get back to this one. This is your runner, yes or no? Means this is your runner. So what is my hydraulic efficiency? Is the ratio of power given by water to the power given by turbine. So here your water is containing some power, means this is the, here whatever head we have, corresponding to this we have some power producing capacity, right? And then your runner will generate some power. So the ratio of these two means what is the maximum power we do have, and out of which how much we have got converted. Got the idea that initially we must be having some power at this point, and then this power is get converted into whatever power your turbine was able to generate. So then the ratio of these two is called what? Hydraulic efficiency. Got the idea? So can I write down this is the ratio of hydraulic efficiency is the ratio of powered runner power, very important efficiency if I talk about runner power, runner power divided by whom? Divided by water power. Means whatever the water was carrying power with it, and runner must have developed some power, then the ratio of these two is called what? Hydraulic efficiency. Okay, so this is equal to what? Water power is nothing but rho q g h. Okay, we know this part. And what is the runner power? We have developed expression for this one on the uh, previous class. So it was what we developed was the rho q into vw1 u1 plus vw2 u2, vw1 u1 plus minus vw2 u2, depending upon the sign of this one, means vw1 is in the sign of vw2 or opposite to it. So usually we, what do we do is that we take it as plus minus. So this part we have done in the last class. So we, this is just an extension of what? That runner power we appreciated. This was rho q vw1 u1 plus v plus minus vw2 u2. And what is runner power? Rho q gh. So my hydraulic efficiency formula reduces to whom? vw1 u1 plus minus vw2 u2 upon gh. And what is this h? H, h is the net head. Net head. Why? Because this was the power water was carrying at that point where runner was installed. Got my point? This is the power. This is the h which was available at the runner inlet. Okay, so this is the hydraulic efficiency. So this h I am talking about, this h, this h, this one. Fine. Next. Next is see, one confusion you must be arising in your mind, that from where to calculate this h, means this datum is here but nozzle is here, so the nozzle's datum become this and this part. See, usually what happens that there is very lesser difference between means nozzle inlet and tail race part. So that is why, in order to make it clear, I have drawn like this, but there is no such big difference between this h and h from this point. Okay, so there's no big difference, so that is why I have written from here. But the initially what happens then, this is treated as what? This is treated as datum, and from these points things are calculated. This is not of much importance, but you should know. Second thing is hydraulic efficiency. I hope all of us know now. And second thing very important is volumetric efficiency. Next is volumetric efficiency. Volumetric efficiency. What is volumetric efficiency? This is the volume per second which strikes the runner, and this is the ratio of, see what happens. Let us get back to this point. See, now the volumetric efficiency is your nozzle is supplying some water, yes or no? But at this point, some of the water will strike and some of what the water may not be able to strike this runner. So the ratio of these two means what maximum could have struck and what is actually striking. The ratio of those two will be volumetric efficiency. So volumetric efficiency becomes volume of water, volume of water, volume of water actually striking runner, actually striking runner divided by volume of water, volume of water supplied to the runner, supplied to the turbine, supplied to the turbine. This is that fact, na? Means what is the amount of water which is striking the runner, and what is the amount which was supplied to the turbine. Okay, so this is volumetric efficiency. And what is the problem here? Why we are this value is not 1? Because if q, and we can write down that this is per second, this is also per second. So q, if q is the volume per second supplied by z, q is the volume per second supplied by z, then delta q, this is the leakage loss, this is the leakage loss, means this is the amount of water which is being leaked. Then what is volumetric efficiency? This is q minus delta q divided by q. Means there is some leakage. Now we understand there can be some leakages. So those leakages are not striking the whom runner. So let us account them somewhere. So this is called what? Volumetric efficiency. Very, these two terms are very important. Now third part is volumetric efficiency we have seen. Third is mechanical efficiency. Mechanical efficiency. See, what I told you initially is my job is to convert hydraulic energy into mechanical energy. Now what happens is that when your water strikes the runner, your runner is generating some power, but that runner is shifted, is lying on a shaft, yes or no? So that shaft is finally getting you some power. So what your runner is able is to generate, and what your shaft is getting, actually there's different. So that ratio is called what? Mechanical efficiency. Means the power delivered by the runner and what is the power transmitted to the shaft of the turbine. So what I am writing down, the mechanical efficiency is, I hope all of us are getting. Any confusion, anyone? Quickly tell me. Yeah. Okay. Now, so what is hydraulic efficiency? This is power delivered by water, delivered by water to the to the runner, and this is power at the shaft of the turbine. So can I write this one as shaft power divided by runner power? Okay. So mechanical efficiency is also done. And now the very important thing is overall efficiency. Overall efficiency. Overall efficiency. This is the ratio of, see, in final thing, what you are getting is shaft power. Yes or no? So final thing I am getting is shaft power. Yes or no? So this is what is available to generate the electricity, and initially what we had is water power. This is now overall na, means finally what we are getting, and initially what we supplied. Initially we supplied water power, and finally we are getting water power. So this is, can we write down shaft power upon water power multiplied by, can I do runner power by runner power? And can you see that this is shaft power upon runner power? And can I see there is runner power upon water power? So just now we have seen shaft power upon runner power is mechanical efficiency denoted by neta m. So can I write down this one as neta m? And runner power upon water power, can you recall what was that? Runner power upon water power was hydraulic efficiency. So if somebody asks me what is overall efficiency, so what I'm going to tell him immediately is that overall efficiency is nothing but mechanical efficiency multiplied by hydraulic efficiency. I hope efficiency parts are clear. Okay. Now, so let us now quickly uh, and see if sometimes this is neta volumetric is also given, neta b, this is neta b. If this is also given now, you simply what do you do? If this is also given, then your overall efficiency is the ratio of is the multiplication of all of these three, means neta m, neta h, and neta v. Okay. So can I see that first thing what do we have is water power. This is greater than whom? Runner power. And this runner power is greater than whom? Shaft power. And this shaft power is greater than whom? Generator power. Yes or no? So this we are not worried about, means what is generator power. Why? Because my job is done at the shaft power. So water power greater than runner power greater than shaft power, and this is greater than what? Generator power. Now, classification of hydraulic turbines, important part, classification. See, how do we classify it? First thing is first thing is based on type of energy at inlet. Type of energy, and this is very basic definition, means this is the very basic classification, and this is the only which governs the whole turbine. So type of based on, first thing is type of energy at inlet. When type of energy at inlet, based on this fact we have, first thing is impulse turbine, impulse turbine. And we have second thing is reaction turbine. Impulse turbine and reaction turbine. Then we have second thing, sometimes there can be questions based on this classification, but very easy question. If it will be, then it will be very easy, but we should know. So second thing to classify is that direction of flow through runner. Direction of flow through runner. Then it can be first is tangential flow turbine. Tangential flow. Second thing, it can be radial flow. I will tell you what are these things later on. See, tangential means water is hitting tangentially. Radial means that it is, I will tell you later on with the figures. And third is axial flow. Axial flow. And fourth one is mixed flow. Means mixed flow means what? It will come in the, one direction and it will go in another direction. Radial flow, what do I mean? That let us say that turbine is like this. Then what happens is that water will come at this point, and from this point to this point this will turn out. From this point to this point it will get out. This point to this point means, what do I see? That this is water is flowing radially, right? And what is meant by tangential? Tangential means what? That you are suppose you are hitting this one, that means you are hitting the veins, these veins tangentially. You are hitting these veins tangentially. Okay, so how tangentially it is hit? This is the way you are hitting it tangentially, right? And axial flow means what? That if this is the runner axis, means here what do we have? The runner, this is in this direction, but when I say that the runner is in this direction and the flow is like this one, flow is like this one, then I can say that this is axial flow. Okay, and mixed flow means what? That it will come in this, come radially and go out axially. It will come out radially, go out axially. We'll talk about these things later also. And third thing is according to the head of inlet. Head of head head at the inlet. Head at the inlet. What is the one? First is high head turbine. High head turbine. Second is low head turbine, or we can say medium head turbine. And the third one is low head turbine. Okay. And the fourth division is specific speed. Specific speed, again these are not that important. Means we can say that low specific speed, medium specific speed, and third one is again high specific speed. I will give you a chart. That chart will help you to draw the conclusion. But only these, if I know this one, then these three classifications follow. These three classifications follow the first one. Okay, so the first thing I'm going to study here now is impulse turbine. What is that? Impulse turbine. Impulse turbine. Clear? Let us understand what are the facts about impulse turbine. See, this is impulse turbine is, this is a high head tangential flow impulse turbine. This is also called Pelton wheel. This is also called what? Pelton wheel. Okay. And this is high head, high head and tangential flow turbine. Okay. See, whenever we have energy in case of turbines, then what do we have initially is, can we see that, can we see here that the water was stocked somewhere, yes or no? So this water, if comes here, then it had some head, yes or no? If all of this head is get converted into kinetic energy, then I say that all of my energy has what got converted into kinetic energy. Then only energy at the inlet, means when I hit these things, is the kinetic energy. Then I say that I have so much of impulse with me, right? So that is why it is called impulse turbine. And one thing I have told you, reaction turbine. So what happens in reaction turbine is that all the energy will, means here your what do we have is the pressure energy, and this pressure energy is get converted into kinetic energy, and then these are hitting these vanes. But what happens in another case is that all these pressure energy is not converted into kinetic energy, but partially, means I will be left with some pressure energy and the kinetic energy as well. Then it is called reaction turbine. So what happens in the impulse turbine is all my pressure energy has got converted into kinetic energy before hitting these vanes. So that means that I am having too much of impulse with me. That is why it is called impulse turbine. Okay. And high head means what? That these are turbines, when these turbines are used when your dam is at too high level, means, or not high level, I should say. What do I say is that your water storage level is too high. Got the idea? Then these turbines are used. Okay. Yeah, so these three are important thing: impulse turbine, Pelton wheel, high head, tangential flow. And what is the very important is that all the pressure energy pressure energy is converted into kinetic energy where at the nozzle. Okay. Kinetic energy at the nozzle, or I should say that at the inlet of the turbine. Then what happens? Then 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 can I say that before penstock and after penstock, at both of the cases, sorry, not penstock, before tail stock and after the turbine, means before turbine and after turbine, you just understand this thing, that if all my pressure is converted into kinetic energy, then what do I mean? That here and here, both of the things are nothing but atmospheric pressure. Here also we will be having atmospheric pressure, and here also we are having atmospheric pressure. Why? Because I have converted. Here I cannot say we have atmospheric pressure. Here we have more value compared to atmospheric pressure. But here what did I say? That I have converted all my pressure energy into kinetic energy. Then what do I mean? That I am having only kinetic energy here. That means my pressure is at atmospheric level. Similarly, when the water passes through the tail race, it is at atmospheric pressure. Got the idea? Okay. So where I was, yeah. So pressure, what I can say is that how do I say, the pressure at inlet, pressure at inlet and outlet is what is atmospheric, is atmospheric. Then my meaning to say is that if I am having inlet pressure at inlet and outlet as atmospheric, then whatever change or whatever turbine is able to do, that is not due to pressure change, but that is due to what, due to the impulse generated by whom, this kinetic energy. Okay, now this part. Now let us understand few important parts of Pelton wheel. This is also called Pelton wheel, sometimes Pelton turbine, so we should not get confused. So I am writing down now. So what happens in, once more I am just finishing this part, like what is impulse turbine. What happens here is that water is supplied by penstock from reservoir, yes or no, and then this water flows through the nozzle. Then the all of the pressure energy is converted into what, kinetic energy, with the help of whom, with the help of nozzle. And now the nozzle is able to what, generate jets, and these jets are striking what, striking the wheel which is mounted on uh, a runner. And this strike between whom, between the jet and the vanes, between jet and the vanes is able to generate what, generate very high amount of force. And this high amount of force is generated in very lesser time. So that is why this is called impulse also. And due to this impulse your runner is able to rotate, so that is why I call it what, impulse turbine. So I hope the idea is clear now. Means that there is some jet, and these jets are flowing through, hitting the there is a wheel, and this wheel is shifted on what, on a runner. And on this wheel we have number of vanes. So as soon as this jet strike these vanes, these are very what, in the very less time. Why? Because this is having too much of energy. That is why this is able to generate impulse force in very less time. Impulse itself means in very less time. Okay, now important parts of, or important components of impulse turbine. Impulse turbine or Pelton wheel, these two are same. Sometimes they will directly say you that in a Pelton turbine, so you should able to understand that they are talking about whom, a impulse turbine. So first thing, penstock is available for everyone. So penstock, we know that what is penstock, these are the large diameter pipes which carry the water from the reservoir to the turbine. So there is no need to write. Penstocks means what, large diameter pipes which carry water from what, from reservoir to whom, to turbines. Simple, to turbines. And these are what, these are large diameter pipes. Okay, penstock. Second thing is spear nozzle. Spear and nozzle, what are these things? Nozzle, we understand what is spear. See, at the end of the penstock, at the end of this penstock there's a nozzle provided, right? So which is converted pressure energy into kinetic energy, this we know. Now what happens is that through this nozzle, let me draw it again. through this nozzle we are supplying fluid. Okay, so sometimes we need to control the rate of flow also, yes or no. Sometimes we may need higher amount of flow, sometimes we need um, uh, decrease decreased amount of flow. So in order to control that, we have a spear fitted inside the nozzle. So what happens that this is the one which is controlling the area of flow, yes or no. This is the one which is controlling the area of the flow. Yeah. So if I put it back, means if I take it on the backward sides, then we will be having more area of flow. That means their flow rate will be increased. And if I move it forward, means in this direction, that means I am restricting the area of flow. So the what is the sphere? This is that sphere which is used to control the area of the flow, area of the nozzle. Okay. Heard. Third thing is runner. Runner, this we know. The runner is nothing but this is the rotating unit over which this is the rotating unit. This is the rotating unit over over which uh, what a number of cup shaped cup shape bucket cup shape bucket or what do I say is two hemispherical shape buckets are installed or or two hemispherical hemispherical shape buckets are installed. Okay, and what is the advantage of two bucket shapes? We'll talk about it later. Means two bucket shape advantage we should write here, and I will tell you later. Advantage is that two two hemispherical two hemispherical buckets buckets helps to cancel out the axial, helps to get rid of what, get rid of axial thrust. That means there will be no Fy. This Fy will be directly zero. I will tell you how. And the fourth thing is casing. Third we saw na runner, and the fourth is casing. And then we'll move to its velocity triangle. So casing, this is what this has not any hydraulic function. Means it is just a cover to avoid the splashing of water. Okay, so it is used to avoid splashing of water. Okay, now. And one more thing is that there is braking jet or back nozzle or back nozzle. What is it? See, when you are running a turbine, but let us say that there is some failure or you need to immediately stop your turbine. See, then what you can do is that you will cut your supply. But even though you cut your fluid supply, but due to inertia the runner will keep on rotating. Yes or no? The rpm of runner is very high and it has too much inertia also. That means due to that inertia it will keep on rotating. But let us say that you need to immediately stop because there is some mechanical failure and which can get accelerated. So what you need to do at that time is that you are having braking jets. Braking jets means what? See, let us say that this is the jet which is helping to generate the power. Then braking jets, what do they do is that they will attack in reverse direction. Like suppose these are rotating in this direction. Like if this is rotating in this direction, then if I supply the jet in opposite direction, then what will happen? That it will reduce its speed. Getting the idea? Like if there is some let us say clockwise rotation, but if you supply something so that it starts rotating anti-clockwise, but it will not immediately start rotating anti-clockwise, but the effect of clockwise will get reduced. Yes or no? Why? Because you are supplying force in opposite direction or opposite to the direction of motion. So these are those braking jets or back nozzle which will help you to put the turbine at rest immediately. Yes or no? So it is used to bring runner runner at rest runner at rest as quickly as possible. As quickly as possible. Okay. Now let us move to whom? Velocity triangle. So two hemispherical na. So what is the shape of bucket? The first thing I am drawing here is the shape of bucket. The shape of bucket is something like this. This is very important. If you understand the next few things which I am going to tell you here, then there is no problem in means numerical parts. Okay. So what happens in the impulse turbine is that your fluid will come and attack this one at this point, means tangentially attack this one this at this point tangentially. Then we have already seen we have v1, means this is the fluid velocity with which this will come to this point. And I have told you that we have velocity of the wheel also, that is u, means with some velocity with some u the wheel is also rotating. Yes or no? So this is that velocity. Then the difference between these two is nothing but what? Relative velocity. This is that part, relative velocity. This is u1 v1. And the tangential, what was vw1? World velocity or tangential component. But here since it is attacking tangentially, that means this is the that tangential component. Clear? And what? The deflection angle we have seen na? So this is that deflection angle. This is delta we have seen. Okay, now after it has attacked, the half of the fluid will flow through this direction and other half will flow through this direction. So at this point let us see what happens at this point. So first thing is that fluid will flow through this direction. Yes or no? So this is the velocity with which it is exiting, and it will exit through which velocity? Through the relative velocity. Why? Because this is also moving, and the fluid which has come to the picture has also got some velocity. That means this is exiting with the relative velocity. That velocity is vr2. How do we understand it? Like if you jump from a stationary train and you jump from a moving train, do you feel the difference? We feel the difference, yes or no? Why? Because at that time we are jumping with the relative velocity, and initially when the train is stationary, I am jumping with my only with my on velocity. That is the difference. So here that that means I am exiting with what velocity? Relative velocity. Okay. And then we have u in this direction, u2 or u1, oh sorry, u2. And then v is nothing but v. What do we know about v1? This v1 is nothing but the sum of u1 plus vr1. Yes or no? Similarly, the v2 will be nothing but the sum of v2 and ur2. So this is that v2. Yes or no? Yeah. This is V2, and this V2 has two components. We have seen one is flow component. This is responsible for flow. This is called Vf2, and the tangential component of this V2. This is called Vw2. The tangential component of this V2, this is the axial component of this V2, which is also called flow velocity. This is the absolute velocity at the outlet. This is the relative velocity at the outlet. This is the uh, wheel velocity. Yes or no? So this angle, let us say if this is phi, then this angle is also phi. This angle is also phi, and this we have denoted as beta. And what did we knew about it is that it is the angle between whom? V2 and Vw2. Okay. And in this Pelton wheel, which things are Pelton wheel, which things are fixed? What things are fixed? First thing is u1 is equal to u2, and this is equal to u, means the tangential velocity of the wheel at entry. See, this I have drawn. What? This is nothing but a vane, but this is fixed on a wheel. So at that wheel, this velocity at this point and the velocity at this point, means the wheel velocity will not get changed. Why? Because this is very lesser, so there's no radial change. That means there is no change in u. So what is considered that u1 means the velocity of wheel at the inlet and at the outlet is same. So that is why I have written like this. Okay. And here we have no nozzle angle at the inlet. Yes or no? So that is alpha is equal to 0. This we have seen. Similarly, theta is equal to 0, and vf1 is also 0. Why? Because the velocity has no axial component, right? The all of the velocity has tangential component. So can I write down that v1 itself is vw1? See, in the question they will give you in the form, like they will ask, let us say that they will give you the tangential velocity at the inlet, then you should immediately know that this is the absolute velocity also. So if we know that what things were zero, what things has the relation between them, then only we'll be able to do. So we should know these facts, that in tangential flow turbine or in an impulse turbine or in Plton turbine, what are these angles and what is the relation between the velocities, different velocities. Okay. Okay. So theta and alpha we knew, right? So alpha was nothing but nozzle angle. Nozzle angle is 0, and theta is also 0. Why? Because there is no vane angle. Here we have no vane angle. Na? So vane angle at the entry is 0, but here we have some vane angle at the exit. Why? Because this is, see, entry point is tangential now, so there's no vane angle at the inlet. So directly I can say theta is also equal to 0. Okay. Now next few things, very important. Next few things are very important, so please follow carefully. So first thing is u1 is equal to u2 and this is equal to u. So that means this is nothing but pi d n by 60, and d is nothing but the diameter of the wheel, and n is the number of revolution per minute of the wheel. So first thing we know should know this. Second thing what we should know is that if the vein is smooth, if the vein is smooth, if the vein is smooth, then Vr2 value is equal to Vr1. And if vein is not smooth, that means it is a rough vein, then Vr2 is equal to K times Vr1. Okay. And next thing is velocity of jet. Velocity of jet. So velocity of jet, how do we find out? See, will how do we find out velocity of a jet is, see, total power at inlet is, power at inlet is rho gq times h. Yes. And total power at the exit means power at inlet of nozzle, and power at the outlet of nozzle, power, or I can say that power at exit of nozzle. This is half of m dot va square. Why I am writing like this? Why? Because I told you that at nozzle inlet we have some water, but all of them have got converted into what? Kinetic energy. And if the nozzle efficiency is 100%, if the nozzle efficiency is 100%, then what happens? These two are essentially equal. That means, can I write down that rho g q h? Rho g q h is half of m dot v1 square, and can I write down m dot as rho q? So this rho q and rho q will get cancelled out. So can I write down this is gh is equal to half of v1 square. So from this one, can I write down that v1 is square root of 2gh. Small h and capital H we are confusing. You follow just one convention. Okay. So this is 2gh. Okay. And see, sometimes they will mention you that coefficient of velocity they will give you. That means nozzle is not 100% efficient. If nozzle is not 100% efficient, then they will give you CV, which is called coefficient of velocity. Coefficient of velocity. If coefficient of velocity CV is given, then your V1 will become CV times square root of 2gh, and this CV is always less than 1. Okay. Now what is discharge? Q value. Discharge means Q value. This Q is area times this velocity. Okay. And what is this area? Area is pi by 4 times d square. And what is this d? D is nothing but diameter of jet. Diameter of jet. And this diameter is at what place? At the nozzle outlet, or A is nothing but the area of the jet. Area of the jet. Okay. So till this point things are clear. Now power. So water power or hydraulic power, we know that this is rho g qh, this we know. Now what is runner power? Runner power is, we know that this is rho q vw1 u1 plus minus vw2 u2. So let us look after that what will be the sign here, plus or minus. So let us first go back to the velocity triangle, and can you see that vw1 is in this direction? VW1, the direction of VW1 is this. And can you see that the direction of VW2 is something like this? Why? Because the component of this one is the one component is this, second component is this one. That means VW2 is opposite to the direction of V1. So minus and minus will get cancelled out. So this will become plus. So this is rho Q VW1 U1 plus VW2 U2. Okay, so this is your runner power. And moreover, I need not to write U1 and U2 separately. Why? Because U1 is equal to U2 and this is equal to U. So can I write down now runner power as rho Q into VW1 plus VW2 multiplied by whom? U. Okay. So your shaft power is equal to, okay, leave it. So runner power we knew. Now, what is your shaft power? Shaft power is runner power minus of mechanical losses. Okay. So efficiency. Let us now find out efficiency and one very important condition for this one, efficiency. Few more things and then we are done with Pelton and then we'll solve the problems based on Pelton gate. Shaft power is runner power minus mechanical losses, efficiencies. Efficiencies. First thing is hydraulic efficiency. So this is what runner power divided by water power, and runner power just now we have seen is rho Q VW1 plus VW2 multiplied by whom? U divided by what is runner power? Rho Q G times H. So this is also equal to half of m dot V1 square. Yes or no? Yes. Why? Because this is converted and V1, this is applicable when efficiency of nozzle is 100%. That means the nozzle is able to convert all of the power at the inlet into kinetic energy, right? So can I write down hydraulic efficiency? This is equal to 2 times, if I use this one, then can I write down this one as 2 times VW1 plus VW2 multiplied by U upon V1 square. One thing. Next. We knew that VW1 is equal to V1. Yeah. And can we see from the velocity triangle? Can we see from the velocity triangle where we have drawn here? Can see that VR2 cos phi, VR2 cos phi, this is equal to whom? U2 plus VW2. Yeah. So, and one more thing is that VR1, VR VR2 is K times VR1 if this is not smooth. And can I write down this one is K into VR1 is what? V1 minus U1. V1 minus U1. Okay. And VW2, can I write down? This is VW2 where this is VW2 is here. So can I write down this one as K times V1 U1 cos phi minus U2? So VW2 here I am writing down so that the whole term can be written in one line. So can I write down VW2 is VR2 cos phi minus U2 and VR2 value is K times V1 minus U1 into cos phi minus U2. and anyway the u2, these things are same. Okay, so final value of your vw2 is k times v1 minus u cos phi minus u. Let us use this when where here. So I am finally writing down here that vw1 is v1 and vw2 just now we have derived is k times v1 minus u1 cos phi minus u2. Okay. Now, what is your hydraulic efficiency? Just now we have seen my hydraulic efficiency like this. So let us put these values here. So this will become 2 times of 2 times of VW1, and VW1 is V1. VW1 is V1 and plus VW2. VW2 is K times V1 minus U1 cos phi minus U2 multiplied by VW1 U1 multiplied by U divided by whom? Divided by V1 square. So for given V1, for given v1, why I have written this one like this, that now my whole hydraulic efficiency is in terms of what? My velocity, my inlet velocity, and the velocity of whom? Velocity of runner, I can say. So for given v1, what is the relation between the runner velocity and my inlet velocity? So for given v1, only thing variable is u. So for maximum efficiency, can I do that d neta upon du is equal to 0? So when we do this, then I can say that this is 0 is equal to 2 times of v1 minus 2u1 2u1 into 1 plus k cos phi 1 plus k cos phi divided by v1 square. So using this one, you will reach to whom that u is v1 by 2. See, this is important. The like derivation you will anyway able to do. Means just differentiation part is there, na? So v1 is constant, just differentiate it with respect to u, and we are done. Okay. So this anyway became 0, and this u will come inside, and this no big deal to differentiate it. So when we differentiate it now, finally we are able to get that u is v1 by 2. This is very 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 important relation. Okay. Then what is the maximum value you are able to get? So what is the maximum value you are able to get when you put this u is v1 by 2 into which equation? Into this equation. Then you will get that neta max is nothing but 1 plus k cos phi divided by 2. Okay. So this K came when? This K came into picture when the vein was rough. If the vein is smooth, then what is the maximum efficiency you can achieve is 1 by 2. Tell me yes or no. If this is the smooth vein, then what is the maximum efficiency I can get? This K will become 0. Then the maximum efficiency I can get is 1 by 2, that is 50%. Okay. Now, next few efficiencies. One very important efficiency is blade efficiency. Let us understand this one. Blade efficiency. What is this? Blade efficiency. See, neta blade. This is equal to, please look carefully what I am writing down here. This is equal to kinetic head, kinetic energy head, kinetic energy head at inlet to the blade, at inlet to the blade, blade minus kinetic energy head kinetic energy head at outlet outlet to the blade to the blade divided by kinetic energy head at inlet to the blade. What do I mean? That if your blade is able to utilize all of the kinetic energy head, then your blade is 100% efficient. Otherwise, your blade is not 100% efficient. Why? Because some of the kinetic energy is anyway lost. Yes or no? So, what is the blade efficiency? Neta blade. This is equal to V1 square upon 2G. This we know now. This is kinetic energy head minus V2 square upon 2G divided by what? Divided by V1 square by 2G. So when you solve this one, this is nothing but V1 square minus V2 square divided by V1 square. This is the blade efficiency. Okay. Now few more things and we are done. Few more things and we are done. I hope all of us are getting. So if you follow these things now, if you understand these things, then there's no difficulty in understanding anything from now on. Means the problems you will be automatically able to do. There's no difficulty that you will not be able to do. So only thing, you understand the velocity triangle, you understand how efficiencies are written, you understand what is the correlation between the given velocities, and then we are done. Sometimes they will give you that this is the for the maximum condition, they will mention you that the turbine is running at its maximum condition, then you should be able to derive that okay, they must be telling us that u is v by 2. So such kind of scenarios will be given to you. So sometimes you have to use your own sense to find out. Okay. Now, another thing is speed ratio. Speed ratio. Speed ratio. This is this is the velocity of wheel. The velocity of wheel is given by what? That u is equal to 5 times square root of 2g h. Okay. And this phi is called what? Speed ratio. And what is the range of this speed ratio? This is lying somewhere between 0.45 to 0.47. Okay. And flow ratio. Flow ratio, similarly, what I can do is that I can write down my flow velocity, my flow velocity, my flow velocity Vf1 is kf times square root of 2g h, and this Vf is flow ratio. Flow ratio means what is the flow ratio here? Kf is the flow ratio. Okay. So here we have seen that Vf1 is equal to 0. So the flow ratio Kf is directly 0. Got it? Okay. Next thing is jet ratio. This is equal to the ratio of pitch diameter of the Plton wheel to the diameter of the jet. Means jet ratio m This is equal to capital D upon small d. This is what? Capital D is diameter of the wheel, diameter of the wheel, and what is small d? This is diameter of the jet. Diameter of the wheel divided by diameter of the jet. Okay. So what is number of vanes? Means what is the number of vanes we should be using on the wheel, number of vanes. So this is denoted by whom? Z. This is equal to 15 plus 15 plus m by 2, 15 plus m by 2. So this is 15 plus d upon 2 times small d. Okay, so we can also write down that this is nothing but 15 plus 0.5 m. So number of vanes, this is the formula. Okay, and then width of vane, this is equal to 5 times of the diameter small d, and depth of vane, this is equal to 1.2 times diameter of the vane. And what is the number of jet? See, jets can be multiple, like there can be 5 6 nozzle operating simultaneously. Then what is the number of of jets what is the number of jets in multi multi-jet multi-jet Pelton wheel? This is equal to discharge total discharge from penstock divided by what? Discharge from one nozzle or discharge from one jet? Discharge from one jet. Okay, and this is greater than equal to 6. No, this should not be greater than equal to 6. Okay, and this delta value, the deflection angle value, this is somewhere 160 to 170. Okay, and second, one more thing important is the frequency. So the frequency f is p. P is number of poles, number of pairs of pole times n. N is the revolution per minute of the wheel divided by 60. So this is frequency. Okay. So F is P is number of pair of poles. F is P into N by 60. So this is all about Pelton wheel. So based on these facts, there will be having questions that, okay, tell me what is the force value, what is the discharge value, and other things. Okay, so we'll solve questions based on this fact, and then our Pelton wheel is also done. Okay. Okay. So you guys are writing simultaneously these things in your notebooks, right? Or not? Yeah, you should. This is the good practice that you are writing. Otherwise, this will be very difficult. Okay. So should we solve questions based on this? Okay. So let us solve one question. Let us solve one question. So I hope you are sitting with calculators. I will write one question and we'll try to solve it. Okay. So the question is, first question, I'm writing down one question here. The question is, a Pelton wheel has a mean bucket speed of speed of 10 meter per second 10 meter per second with a jet of water flowing at the rate flowing flowing at the rate of 700 liters per second under a head of under a head of 30 meters 30 meters. The buckets deflects the bucket deflects the jet jet through through an an angle of 160 degree. Then you have to find out what is the power given by given by water to the runner. And the second thing is hydraulic efficiency of the turbine. Hydraulic efficiency of the turbine. And they have given that assume CV value as 0.98. Okay. So first thing is to find out what is the power given by water to the runner. So what is that power given by water to the runner? Do we remember? Yeah, this is nothing but power given by water to the runner is rho q VW1 VW2 into U. VW1 plus VW2 into U. Yes or no? So first thing we need to solve in these kind of questions is to write down the given data. So then only you will understand that okay, these things are given to us and what is to be find out. So it has mentioned that u1 is equal to u2 is equal to u. This value is given as 10 meter per second. If you look at your copy, please write this question in your copies, then only you will be able to solve. Otherwise you will not cope up that what was given. Okay. And then it has given the flow rate is it has given now that flowing at the rate of 700 liters per second. So this is nothing but q value. So can I write down q value? Q value is 700 liters per second. That means this is nothing but 0.7 meter cube per second. Okay. And head of water h, this is given as 30 meters. Okay. And it has also mentioned that delta value is 160 degree. So in the velocity triangle where we have phi, can we see when where we have phi? See, I'm just drawing the half of the velocity triangle, means half of the bucket, means it is automatically assumed that there is bucket here also. So in the velocity triangle, we have seen now that we had some phi here. Yes. So this phi was nothing but the same phi here. Okay, so this phi is same. So this angle they have mentioned is 160 degrees, so this automatically is 20 degree. So this angle they have directly mentioned that this is 20 degrees. See how we have reduced to this point. They have mentioned this one, but in order to find out this one, we have reached to whom, that initially how velocity triangle was developed. So this angle is 20 degree anyway known. And what is coefficient of velocity? Cv value is given as 0.98. So now first thing is to find out VW1. Why? Because in the runner power we have VW1, U1, U2. VW1, VW2 and U. So U anyway we know. So what is VW1? VW1 is V1. And what is V1? V1 is CV times square root of 2GH. And CV is given as 0.98 and square root of 2. G is 9.81 and H is 30 meters. So what is V1 value now? V1 value is 23.77 meter per second. So one thing we know now is V1. Next thing is what is VR1? VR1 is V1 minus U1. This we know now. This we know that this is V1, this is V1, this is U1, and this is VR1. This is VR1. So V1 value, this is we have find out 23.77 and this U1 value is 10 meter per second is given to us. So VR1 is the difference of these two. This is 13.77. Okay. So now let us draw the velocity triangle, upper velocity triangle, means velocity triangle at the exit only. So velocity triangle at the exit only. So this angle I know now is 20 degree and this value I don't know. So first VR1 I know that this is 13.77 and there is no information about that the blade is rough. That means I will assume automatically it has smooth vein. So VR2 value is VR1. Very simple. So VR1 now I know that this is 13.77. Very good. And U value I also know that what is U value and what is that U value? U value is 10 meter per second. This I also know. So now I know that this is V2. But my job is to find out VW2 means this component, yes or no? So this component I need to find out. So how do we reach to this point is that I will find out the cost component of this one and then the difference of these two will give me the VW2 value. So the cost 13.77 times cos 20, this value is 12.94. This value is 12.94. So this value VW1, this is VW1 now. So VW1, can I write down that VW1 is VR2? If I write down in terms of word means notification, so this is VR2, this is phi. So can I write down VR2 cos phi minus U? This is U. So can I write down this one as VR2 cos phi minus U and VR2 cos phi, this is VR2 cos phi, this is 12.94 and U value just now we have seen that this is 10. So VW1 is 2.94. So now I can find out that what is the work done by Z or the runner power. Yes or no? So how do we find out? that this is nothing but rho q vw1 u1 plus vw2 u2. So rho value is 1000, q value is 0.7, vw1 value is equal to v1, which is equal to 23.77, and plus vw2 value just now we have seen is 2.94, and u value taken at common is 10. So when we will solve this one, then we'll get that this value is 186,970 joule per second, joule per second. So this is in watts. Okay. So in order to convert it into kilowatt, we'll divide it by 1000 depending upon the unit asked to us. So this is this much kilowatt. Okay. And what is hydraulic efficiency? Hydraulic efficiency is nothing but we knew that just now we have derived. Now this was 2 times of VW1 plus VW2 multiplied by U upon V1 square. So this is equal to 2. VW1 value is again V1, and V1 value was 23.77 plus VW2. VW2 value is 2.94 and U value is 10 and V1 value is 23.77, the whole square of it. Then the hydraulic efficiency is 0.9454, or we can say this is 94.54%. Tell me any doubt, anyone? If anyone has any kind of doubt. Clear? So if you follow these breakups the way I have told you, no, then there will be no problem. They can, what they can maximum do is that sometimes they will give you this velocity triangle, sometimes they will directly give you this velocity triangle. So simple na, from this velocity triangle they will ask you something. So simple that they, how how do they make the question stuff is by giving directly the velocity triangle, and they will not mention that what which one is what. Got the idea? Like they will mention you that okay, at the exit of uh, impulse turbine they will give you this velocity triangle, and they will not mention you that which one is what. Like they will not mention what is this, they will not mention what is this, they will not mention what is this, but they will give you sufficient hint to guess that which one is v, which one is u, which one is vf1. So they will give you hint, so you will have to guess that okay, they are trying to mention that okay, this is that. And based on from this given facts they will ask you that tell me hydraulic efficiency, or they might ask you power, or they might directly ask you that tell me this velocity component. Mostly they will ask you velocity component, because they know that if you can find out velocity component, then you can find out any of the other given things. Clear? So this is all about what? Pelton turbine. Then we'll move to what? Francis turbine, which is radial flow turbine. And then we'll move to what? The numerical parts. And then we are done. Okay. So please go and try on solving the questions from which area? The questions from Z area. Why? Because the questions from those areas are very frequent. So I don't want to spoil your creativity. That is why I have not solved the questions here. But please try. Then when you have tried now, then you know that okay, this is the part I am missing, which sir is telling me now. So that is why I have skipped that part. Not skip, I have that part is anyway to be covered by you only. Why? Because the formula, once I have derived this much, I have given so much of time, then problems you should be trying to solving on your own. And once you are solving the problems on your own na, then only this is the time to gain confidence. Okay, so solve ample amount of previous year questions, solve test series, and try to solve everything on your own now, and keep on revising. Then only you will be able to do well. Otherwise, if you are completely dependent that okay, that sir will solve, I will write down, then you are learning nothing. Why? Because in the exam it is you who is going to solve the questions, it is not me who will be solving the questions for you, right? So it is you who is going to solve, then it is you who should get practiced. Okay, so then only you will know that okay, you are stuck somewhere, okay, you are not able to recall something, or you are making certain kind of mistakes, so then rectify it before the exam. Why? Because in the exam your natural habit will get repeated, yes or no? So there is no wishful thinking that you will think that okay, I will not commit any mistake, okay, how I can be so silly. But in the examination our daily habit is reflected. It is not going to happen like that there will be any miracle that the kind of mistakes which you do at your home you won't repeat that at your exam, unless you get them rectified, or unless you at least you notice those things beforehand. Yes or no? So you should notice your mistakes, and when you can notice those things once you are solving the problem. So idea to solve or crack the gate exam is only thing is to solve the questions day and night, and that is it. Okay, clear your concepts in the classroom, solve the questions at your home, ask your doubts, and then you are done, you are on the right path, right? And the frequent revisions, three things, four things we have also talked, and I'm telling you again and again, if you follow this you will definitely get decent rank. Otherwise just listening to the class, just attending the classes and not solving the questions at the home, not attempting the test series, not revising the test series, you will lead you nowhere, right? So please do that, then only this is fruitful, that you are spending time in the night to take the classes, yes or no? So please utilize those things. Okay, okay, done. From fluid machinery we can have a 2 marks questions max. But see, I have told you now, these are the one who decides the rank. Means most of the people they used to leave this. Why? Because they think that this is the 2 mark. But yeah, direct formula application questions, I told you now, that direct formula application just if there will be critical thinking, very few, means that if you are means you have gone through the concept, you will be easily able to apply. There will be no very tougher questions from this area, very simple questions. Application parts are not that difficult, but there are lot of informations, that is it. Means like hydraulic machinery, the IC engines part, the power plant, the questions the toughest questions can be the formula one. But what you can do is that how to reduce the informations, got it or not? Eh, there will be ample amount of information, this velocity, that velocity, this temperature, that temperature, this charge, and number of things. But you will have to you know work upon that what is the useful data, what is the useful data for your question, and how to reach that. This is the struggle in application parts. In the theoretical parts, in the core parts, means like in your SOM part, in your TOM part, and there you have to apply, you have to be critical, like okay, you have to think that. But there direct formula based questions will not be there. But in these parts, means the application parts, like I told you now, that fluid machinery, refrigeration, there we can directly use the formula and we'll get the answer. But the only thing they will leave up to you is that there will be one missing data which you have to find out using the informations which you have collected in your classrooms. Okay, so we should not skip these parts, very simple, these parts are very simple. But this will directly give you 2 3 marks, got it or not? And like these we have 3 4 subjects, 5 subjects, so 2 into 5 makes 10, and this 10 is the one who decides that what is your rank. Okay, so I told you now that what are those subjects in the earlier classes we have discussed. So let me discuss it again. These are those subjects. What are that internal combustion engines, direct formula based questions will be there. There will be power plant. Power plant means steam power plant and gas power plant. Power plants, direct formula based questions. Then we have refrigeration and air conditioning. Mostly there will be formula based. Mostly there will be formula based. Means not directly formula based. Means what do I mean? That there will be a lot of informations, but if you know all the given informations, means if you know that given datas, then one or two datas will be missing, but they can be what deduced from the given information. So these are those subjects. And fluid machinery, fluid machinery, like these I am talking in terms of what, like on thermal areas. So these are those parts, like there can be 1 marks from this area, maybe 2 marks, similarly 2 marks, or maybe sometimes 3 or 4 marks also. Maybe here rac 2 to 4, it can vary from 2 to 4. Fluid machinery, it can vary from 1 to 2, 1 to 2. So see what is the variation, like let us say that the minimum one, 1 2 2 2 and 1. So how much? 2 2 4 and 6. So these 6 you can get very easily, just if you have attended and solved the previous year questions, that is good enough. Okay, so these 6 will if you are able solving these questions in the exam hall now, then you will feel confident that okay, the questions are being solved, yes or no. So we should not skip these parts when it comes to get the good rank. Okay, got the idea? Here questions are simple. I'm again repeating, questions are simple. Questions are simple, but informations are many. Informations are many. Means the number of datas are more. Means this temperature, this exit temperature, this mass flow rate, that mass flow rate, those things will be here. But when you means know how to connect those dots, means how to connect the missing dots, then you are definitely able to solve the questions from this area, and this will definitely help you some good rank. Okay, so please don't skip these parts also. Never think that okay, this is just 2 mark subject. No. Why? Because this 2 marks is going to give you you will get very easily, like just 2 3 chapters and we are done. Similarly power plant, 2 3 chapters and we are done. Similarly rac, 3 4 subjects and we are done. Fluid machinery, 2 3 4 classes and we are done. So these are the ones which will make you the difference in the rank. So please attempt these questions also, and that is why I'm repeating, start solving questions, otherwise this will lead you nowhere. Okay, okay, so come prepared on the next class, and please try to solve the questions from impact objects, and try to find out which are the questions from Pelton wheel and solve that. And then we'll move to Francis, and then we'll move to the one more information is there, we'll do that also. Okay, means dimensional analysis of the turbine. So that is the fourth part. Questions are from those areas also. Okay, so okay, then we'll continue in the next class. Good night.